Good afternoon, everybody. This is your host here, Chapon Shen from Penn State University. This is the second to last webinar of the recent advances in big data, machine learning, and hydrology. Well, the more we go, the less we have left. So today, we are pleased to have Dr. Sean Reed, Data Science Branch Chief of the USGS Water Resources Mission Area, and also Dr. Vipin Kumar, Regents Professor and William Norris Endowed Chair from the Department of Computer Science and Engineering from the University of Minnesota. So for several years, I noticed they've been championing physically guided machine learning. And I'm sure today it's going to be an exciting seminar. So without further ado, let's give the mic to them.
All right, thank you, Xiaopeng. I'm going to be starting the first half of this talk, and then Vipin will be taking the second half. And we're really excited for this opportunity. And thank you to Xiaopeng and to CUAHSI for inviting us to give this talk on process-guided deep learning and some of the applications that we've been working on. So just to, let's see. Okay, there we go. Little hiccup with advancing the slide, but just to set the stage, I think many of us are here because we understand water resources issues are becoming a greater deal for society. The scale at which we're doing research is expanding, and some of these key elements, such as understanding and predicting changes in water quality and quantity at large scales, are becoming increasingly relevant and needed by society. So what we're doing for the remainder of this talk is kind of splitting it in two parts. We're going to focus the first half on water quality itself. So we're going to have an application that focuses on water temperature predictions. And then the second half will be a quantity aspect, looking specifically at surface water extent dynamics. And that's where Vipin and I will split and hand off between those two. So just as another bit of background, in water resources, we have these continuously growing data sets. And I know that many of you on the phone will be familiar with the continuously monitored in situ sensor data access, such as the USGS's National Water Information System or CUAHSI-HIS. I also wanted to point out some of the more variable or heterogeneous data sets, such as the Water Quality Portal, which is a joint project between the USGS and the EPA to bring together records from over 500 different monitoring groups, including tribes and federal, state agencies and academics. And this provides a lot of important data. It's discretely monitored data, so that means typically grab samples in surface or groundwater. Additionally, I think most, if not all of us, are familiar with Landsat and other remote sensing products. Sorry, I keep double advancing these. But something to keep in mind as a backdrop of large data that we can use to apply to water resources questions. And then one obviously large source of data that sometimes we lose sight of is the kind of in silico or synthesized data that large models produce as part of, for example, multiple forecast realizations or simply predictions for the past or for different future scenarios. And I think there's some emerging projects that attempt to make greater use of the information that comes out of these models for improving prediction. And so one of the questions comes up, we're in this big data era. We have all of these data sets at our fingertips. We've got computing and other tech advances that should arguably create kind of a step change in our prediction quality. And so, some of the grumblings about this big data era is why aren't we seeing these returns? Why aren't we seeing predictions take this step change? And one of the ways to approach this question is to engage in predictive methods that can better leverage new and existing water data. And so one of these concepts that Vipin's lab has shown a tremendous amount of leadership over the last 5 or so years is this idea of theory-guided data science models, or process-based or process-guided data science models. And that kind of gets at this dimension of how much information we're really making use of. So our traditional process-based models might build upon a lot of theory, a lot of knowledge that has been developed and collected over centuries. But they may be too rigidly formulated to make use of this big wave of data sources that I mentioned in some of the slides that were preceding this. In contrast, some of these more powerful empirical methods, such as deep learning models, can make a lot better use of these additional data sources, but they really kind of leave alone all of the things that we've developed for these theory-based or process-based models. And I just want to point back to an earlier presentation delivered by Xiaopeng. I think it was 2 weeks ago in the Cyber Seminar Series, where this contrast, this trade-off between process-based models and what was referred to then as big data machine learning models, and kind of this pattern we've been seeing in the literature that really pits these two approaches against one another and says, you know, I'm gonna create a better machine learning model to beat this process-based model, or, you know, I'm a process-based model, or this machine learning model makes bad predictions in a warmer future, for example. But something that we've been working on within this collaboration, and was also pointed out by Xiaopeng, is it doesn't need to be an either-or question. We don't need to leave the power of big data, machine learning on the table to use process-based formulations, and conversely, when we're going about something from a process-based perspective, we don't need to ignore all the potential that more data-driven approaches can give us. So enter this concept called process-guided deep learning models. We're going to introduce how we've built these models in a couple of different ways. The first one is a joint collaboration between USGS and the University of Minnesota with Vipin's group. And then the second is work that Minnesota has led before that collaboration started. So USGS is, of course, interested in it, but did not contribute to that work. And Vipin will take the second half of that talk. So we're focusing on this water quality variable, water temperature. You might ask yourself why. We call temperature an environmental master factor because it is, understanding temperature is foundational to understanding all kinds of things, such as the solubility of gas and what's going to happen with local economically valuable fisheries, and likewise, of course, a strong connection to the emergence of harmful algal blooms as well. Temperature is also monitored quite heavily. We have a lot of existing temperature resources that can give us temperature observations in many locations for the US. So here we've got a map of all the different sites that have some kind of temperature observation, be it a continuously measured sensor that's within a stream, or groundwater, or a lake or reservoir, or a kind of snapshot view sampling across the nation, such as what we get from discrete data in the water quality portal. So we have all this temperature data. We also have these traditional divides into what kind of tools we can use to predict temperature. So on the left here, we have a process-based model. So this is called the General Lake model. We've been working on this open source tool for, in some cases, about the last decade, and finally released this publication and the third major version of the model just a few months ago. Additionally, as you heard from a couple of these Cyber Seminar series, there is a great deal of promise in using deep learning methods to make predictions for variables, including temperature. And I would add that temperature itself has a really great, or provides a really great use case for embarking on these recurrent neural networks, or or long short-term memory networks because of the lag relationships, because of the inertia, because of the seasonal signal that water temperature exerts, and its predictability by these data-driven models. And I'm pointing out these two previous cyber seminars because I hope many of you were able to view those, and if not, and you're interested in a more in-depth look at these methods, I want to point you to those because they're of course both available through YouTube videos that are linked to the site. So the first of these techniques, the process-based lake temperature modeling, a number of us develop methods to use nationally available data sets that describe a lake's water clarity, its surrounding land cover. Of course, it's driving weather conditions, prevailing weather conditions, and we're able to use that to build thousands of process-based lake temperature models that gave us output that was depth resolved. So if you see that heat map plot, surface to bottom of the lake, depth resolved temperature information at the daily, or in some cases hourly time step for about the last 30 or so years. And then you can see the accuracy of all of the temperature data that we compare these models to. So we're pretty excited about this, being able to create a framework that allowed us to build process-based lake and reservoir temperature models really anywhere in the nation. So we can scale up. The downside is that our accuracy just isn't good enough. These process-based models are effective in many systems, but simply put, some of the predictions we're making are not accurate enough for the decision makers to make use of those, and that is specifically related to some of the fisheries decisions about whether to stock fish or move on. So then, of course, we're once again at this situation where we can pivot. We can pivot away from process-based models and use a more data-driven approach to take advantage of that increased predictability. And here we've got an example of a comparison we did by calibrating a process-based model with increasing amounts of data. You can see kind of diminishing returns in the calibration process. So that's the line plot here shown in green. In contrast, as you would expect, a deep learning implementation of a temperature prediction, the more information, the more temperature data you get, it definitely starts to exceed the predictive accuracy of the process-based model. Of course, it goes without saying the downside of this deep learning model is its hunger for data. So if you are not giving it enough temperature observations, its predictions are going to be quite poor. So it's not a model that we would consider is applicable in data poor or unmonitored systems. And just so everyone's aware, at the type of data sparse or data rich issues we have with water temperature, there's a large number of systems that are monitored sparsely. So maybe once a year, maybe if you're lucky, once a month. Very few number of systems that have something like an instrumented buoy that would give us continuous temperature measurements. So most often in these predictions, even in this era where we have more data than we've ever had before, we're often dealing with sparse data conditions, and you can see that in the animation, assuming that's coming through on your end. And so the question is, can we merge these two approaches? So I think, Xiaopeng delivered earlier, you don't have to do an either or. You can potentially integrate one of these approaches into the other, or at least share some of the gains. So this question, can we take the greatest gains from this process-based modeling approach and create these process-guided deep learning predictions? And we want this to obey a number of things. We want this to meet some of the expectations that we have for process-based modeling, such as we want this to be constrained by physical laws. And this is important for temperature prediction because if we're using a model to predict summertime temperatures or predict temperatures in a unseen but warmer future climate, we want that relationship of temperature change to be grounded by the physical reality we have, which is given to us by the conservation of energy. So here we've got an example paper from Jiawei that built this energy budget constraint into process-guided deep learning models. The next element we want from this integrated, this hybrid model is reasonable trust in the predictions we have when we don't have very much data. So this is that situation where most lakes or most rivers, lakes, and streams have sparse or no information for water temperature. So then the question comes in merging these approaches: can an uncalibrated process-based model output provide something useful for deep learning models? And I think I've got a little trying to deal with this lag with advancing slides, but hopefully this shows up here. Okay, we'll get there. Okay, here we go. So this idea that an uncalibrated model, although it is an imperfect representation of reality, if we combine it with observations, can we improve our modeling? And so in order to understand the structure of these, so we have a process-based model on top, we have a data-driven deep learning model on the bottom. We've simplified the structure of these a great deal to highlight some of the similarities of these approaches. So both, of course, have inputs. Both, of course, have parameters. Each have internal computations, and of course, the objective of both of these models is to make predictions. A deep learning model always has feedback, always has to be trained. In a process-based model on top, there is arguably an optional feedback in calibration. So we can parameterize a process-based model, and we can then choose to refine that parameterization through calibration, or we can apply this type of model in an unobserved system, thereby not using a calibration procedure to do so. So this question about what can we do when data are sparse, can we use predictions from an uncalibrated process-based model to act as a replacement for observations, to give us supervised data when we otherwise would have limited or none? And here's where we introduce this bottom box of process-guided deep learning and show the contrasting structure compared to what we had before with deep learning, with just the singular deep learning model. Here we have inputs, which now are the drivers that feed our process-based models. And we have two versions of this. We have the normalized transformed drivers, which go into the neural network. Then we have a secondary set of the actual weather drivers. So this is radiation, air temperature, wind speed, etc. Those are important because we want to track this energy budget internal to this model. We want to penalize this model structure if it's not obeying energy conservation. And then we have this additional element on the right where we're using training, we're using traditional training. So we have observations that are then used to refine, but we have this new concept called pre-training, where the process-based output are used as a proxy for the observations, are used instead of the observations. And this pre-training step gets us to the point where we have a reasonable network built, and we can use that as a starting point for the final training step, which thereby reduces the amount of data that we would need to build an accurate prediction. And I want to point out, Xiaopeng had this test paper where this same concept was mentioned as a potential future avenue. So of course, process-based models can augment data for deep learning models. They can be used to increase supervising data, for example, unseen scenarios. And in our work with pre-training, we've done exactly that. And in these situations, you recognize that if you're using an uncalibrated process-based model for a pre-trainer, that uncalibrated model has no knowledge of the actual observations. It represents a potential scenario back in time, forward in time. We can build as much pre-training synthetic data as we have driver data for. So for example, we could build a model that started in 1950 and goes up to the end of 2100, creating a very rich data set to initialize this deep learning network. Then in the secondary step where we actually train the data set with the observations. So we use these orange data points, which are sparsely measured, to refine the network. Then we move into a testing phase. So the power of using that existing process-based model, which in itself obeys our known physical laws and constraints, is really a great opportunity for these predictions. And so what does this do to our ultimate goal of making better temperature predictions? Well, now we've overlaid the predictions of the process-guided deep learning model in the same scenario where we're giving it increasing amounts of actual water temperature observations and looking at the impact on prediction. So you can see that as we have more and more temperature data, getting to the point where we actually have an instrumented buoy that gives us continuous temperature observations, that the process-guided deep learning model gets pretty close to converging on just the straight up deep learning model. That probably makes a lot of sense why that would happen, because we have so much information that we can effectively reproduce the physical dynamics. But as we move to the left of this plot, as we move into greater data sparsity, so less and less temperature observations, that's where you really see the power of this approach. And if you remember the earlier slides that I had that showed, it's a lot more common for us to be in this data sparse situation in these modeling systems. Even though we're in this big data era, we're still data sparse in a lot of these environmental conditions. So the advantage over our process-based model or over the deep learning model in those types of conditions is really impressive and powerful, and got us very excited about how we could use it. We then went further and evaluated this type of model on something that machine learning models are traditionally critiqued for, which is in some cases, inability to predict out of bounds of the training data. So say, for example, well, I'll just give you the example of the figure B here, where if you train a model based on the coldest 10 years on record, and then you attempt to predict the warmest 10 years on record, or the warmest 5 years on record, traditionally, a machine learning model might not do very well in this, because it might not understand that in these hotter seasons, these hotter years, that evaporation became more important, and thus, it over-predicted the surface water temperature in the summer. And then likewise, an even greater challenge here is shown in panel C, where we only gave the model spring, fall, and winter as training, and then attempted to predict the summer season. And because of both the pre-training elements and the energy budget constraint that exists within the process-guided deep learning model, in addition to actually being trained with observations, the performance of this process-guided deep learning model was better in all of these conditions. And just to point out what panel A is basically the control, as if train and test were similar situations. So kind of a random selection of, did you get a cold year, a warm year, and what are you attempting to predict? So I want to bring this back to the second slide I presented as Vipin takes over this talk. So I've presented the quality examples here. Vipin's going to take over, assuming our handoff is seamless, on the quantity side of things.
All right, I guess I am ready. Should I try to advance the slide?
Yes.
Okay, I'm going to. Yes, it was working seamlessly. Thank you, Jordan. And yeah, this is Vipin Kumar from University of Minnesota. I also have Ankush Khandelwal, one of my graduate students whose work I'm presenting here. This is about global surface water monitoring And again, the motivation is to be able to study the impact of changing climate, human actions, and also hopefully aid in being able to provide the information to the early warning systems. And one of the goals that we are trying to pursue is how you use this technology to help quantify the stocks and flow of water on a global scale. And the other application we see it is being able to come up with calibration data for hydrological model in basins that are largely engaged, which apparently is the case for many places around the world, including U.S. So what is the state of the art in global surface water monitoring? So we have static shapes of water bodies from data sets such as hydrolakes and GLWD, GRAN, and SWVD. And these are, certain number of, like, for example, hydrolake has about 500,000 water bodies, and they exist in a certain shape on a certain date. And on the right side, we have the dynamic information, multi-temporal dynamics, but only at a pixel level. And that, of course, at the Landsat scale, that's coming in from multiple sources. One of them is the JRC Google product, and the other is from USGS. And then for MODIS, again, there are products available that would provide 500-meter data at 8 days at 250-meter resolution on a global scale. But they only provide you pixel-based information and not any information about the water body's extent in any way. Our objective is to be able to basically capture the dynamics of water bodies instead of just capturing the dynamics of pixels. So what we want to be able to do is what you're seeing on the left half of the screen. You see the two water bodies. One of them is showing you simply what, if you saw the pixels from the JRC product, Google JRC product, the blue being water, green being land, and yellow being something that's not known. This is how it will show up. On the right-hand side is exactly what we like to be able to produce, and on the bottom is giving you the time series of that surface water body in terms of number of pixels as it's changing over a period of years. So this is our goal. That is, the idea is that for all of the 500,000 or so water bodies around the world, can we know how they are changing over a period of time? And of course, in general, this would be applicable. The information would be available at a certain spatial scale, like Landsat or MODIS, and certain temporal scale, like for MODIS, it could be 8-day composites or perhaps even possibly daily. And for Landsat, it could be 2 weeks or at a worse resolution like JRC is about monthly. On the right-hand side, what I'm trying to show you is a sort of another objective here. That is, what if I had information at a 500-meter, the labels at a 500-meter resolution from MODIS. This water body that you're seeing here in the second half, but the left corner of the second half, it looked pretty jagged. You can see these. You can see the water body information underneath. The blue is the water body, and then the MODIS pixels are sort of really making it a very jagged body. What we like to be able to see is what you see on the right-hand side, which is a 30-meter map of the same water body. And the intent is that can we construct high-resolution in space maps at perhaps daily scales from using data like MODIS, but which has a very poor spatial resolution, and then can you sort of convert it back into better resolution in space and time? So these are sort of the objectives. Now, why would this thing be hard? And of course, one of the challenges that we have, anybody would face in coming up with these labels, multi-temporal labels for any pixel using satellite data on a global scale, is that there's a lot of heterogeneity in how water and land looks across the globe. And what you're seeing here on the left half of this picture, and the upper portion of it, is the composites, false color composites of these bodies and their areas around them. And you can see the colors look very different from one place to the other in 3 different locations in Africa, in northern Africa. That sort of shows the heterogeneity. And then in the lower portion, you will see in Argentina, the same lake being observed at 2 different times can have very different false color composite, which means the heterogeneity is both in both space and time. So this is one issue that always creates problems for any algorithm that would sort of create labels for land and water across the globe. The right-hand side is showing a bigger issue. Let me see if I can get the animation working. I guess it's not working. It's let me see. That's all right. So unfortunately, the animation is not working. But the big issue here in the data quality is that a lot of time you have missing data, and worse yet, because the data can be of poor quality because of shadows and other disturbances or clouds, you can have wrong labels. So one thing is having missing information, and the other is having incorrect labels, which is even more dangerous. And together, these issues make it very hard to build good quality dynamics on a global scale for water bodies. How are we handling this? We have this approach called ordering-based information transfer. And again, as Jordan talked about, that bringing in machine learning and infusing some ideas from physics. So we call it a physics-guided machine learning approach that helps us create high-quality, high-resolution dynamics of water bodies. So what you saw in the earlier part of the talk was using the constraint like energy conservation and mass balance to infuse into the machine learning algorithm. Here we are infusing something entirely different. What we are trying to show you is that the water bodies are formed in a cavity, which you see on the top right corner. That means each location in a water body would be at a certain elevation, like A, B, C, D. A is at a higher elevation than B and C, and which means that if A is labeled as water, then B cannot be labeled as land. So this sort of creates a constraint. And the idea is that if this elevation information was available, it could help us a lot in making corrections to the error that would be made by any machine learning algorithm. And oftentimes, this information about elevation is not available, or it's not available at the level of resolution that you would like to have. So the machine learning challenge becomes one of how do you take this concept of the water body is formed in a physical space, and you don't know exactly what that shape is, but yet the machine learning algorithm should be able to make use of this information. So it's almost like an implicit elevation ordering is being inferred, has to be inferred by the machine learning algorithm, and then it has to be used to make the correction. So you can see how that information sort of potentially could be used in the sense that if you look at the two pictures, the same lake that I was trying to show you animation of on the previous slide, you can see for a certain date in February 2012, on the left side, you see the labels created by the JRC Google product. Red is missing, and green is land, and blue is water. And you can sort of feel the water body, and you can see a lot of green inside the water body, so there's a lot of errors. And then you can see also many, you can see errors of both kinds, that is water being labeled as land and vice versa. And on the right side, you will see all of these errors being corrected properly. So this is one major information transfer that's happening across space, which is like you're learning information in the elevation space from the side. And there is also a technique being used here that transfers information across time. That is, if you have information on multiple dates, how do you make use of that information to fix the errors in your labels? Because the water bodies are not only formed in cavity, but they cannot arbitrarily change their shape from one day to the next. So together, these things can be very helpful. Now, the third thing that can also help is the information about elevation, whether it's implicit or explicit, coming in from high-resolution maps that many organizations have created, including USGS. In that case, we have built techniques, again, physics-guided machine learning techniques, that could take a map that is produced by, for example, say MODIS at 500 meter on the left side, and just use this information to be able to create a map that you see on the right side. In a very similar way as in machine learning, we do this process called super resolution, where we take an image, which is very coarse resolution that you see on the left side, and use it to, and use the machine learning technology to convert it into a high resolution image. And again, the idea there is that if you have lots of relationships between the coarse images and fine images, then you learn the fact that there are certain locations in a face that are eyes and certain nose and lips and so forth, and they have a certain structure, and then you learn them, and then you can reconstruct a high resolution image from a coarse resolution image. Now, in a very similar way, you can use physics information to go from a very coarse image that you see on the left side from MODIS, and without looking at any high resolution data, you can convert it into a very high resolution image that you see on the right side. So together, between all of these techniques actually give you the opportunity or the capability to produce very high resolution maps that would depend upon the elevation information you may have and available made produced on a daily scale using data from something like MODIS, which is very, very coarse. So let me show you what we have been able to do using some of these techniques. So here is a link that you see on the slide, which would take you to a global MODIS-based product that would give you tens of thousands of water bodies across the globe. And each of these water bodies is at least 10 MODIS pixels, and these pixels are at 500-meter resolution. And this particular product is created using an 8-day composite data. So that means you will see each of these water bodies at 8-day temporal resolution. And because we're talking about 10 pixels, so you're looking at water bodies that are about 2.5 square kilometers at the equator. And if you go to this website, you will be able to see all sorts of examples of what's happening on a global scale to these water bodies. You can see melting of glacial lakes. You can see changes in river morphology. You can see construction of reservoirs. And all of these three things I will show you very briefly in the next couple of minutes. But you can also see the relationship between the surface water changes that you can see from this product and also groundwater that you can see from GRACE. Very, very high correlation between how the surface water is changing and how the groundwater relationship is, except in certain cases where we see some very interesting patterns driven by agriculture, aqua-agriculture in certain parts of the world, where the groundwater and the surface water are going in the opposite direction. So if this is a summary slide of what you will see out of this 500-meter MODIS product. And if you look at these dots that are sort of spread over the globe, you can see on the top right, at the top left corner, you see a single water body. Actually, it's a Don Martin Dam in Mexico. And you can see its shape sort of changing over a period of time. The shape changing that you're seeing here is some Google time lapse, is a yearly product. But what you get from the website from our product is this time series of how many pixels does this water body has over a period of time, and you can see they're in pretty good sync. On the middle left corner, you will see this river meandering being picked up that are visible from Google time lapse, but they can be identified using these different water bodies that we have that would sort of show both shrinking patterns and a growing pattern simultaneously. On the right side is actually much more interesting thing here. You see on the lower right side is the dam construction. I'll talk about it a little bit later. But in the middle part, on the top right portion, you see these a lot of these orange points that reflect the increasing water bodies, and that all happen to be in the Tibet area, which is home to which is sort of the source of lots of the rivers that feed about 2 billion people in Asia and large parts of Asia. And it's a major concern for the community because of the changing climate. A lot of these glaciers are melting, which is causing these cavities in the mountains to fill up, and these lakes are increasing. And what this product allows you to see is for yourself, see exactly what's happening. So, for example, if I zoom in here, you can see all of these red areas right around the black water bodies. And red areas are the ones that have expanded in size over the last 18 years in the MODIS time period. You can look at another area. You can see more of these. These are all would be visible from the website as you would sort of zoom in. And then if you click on some of these, you'll be able to see the time-lapse images of these water bodies changing over a period of time. So it makes it very easy to see where these changes are and what's happening. And actually, you can very easily compute that in just this area, very small area that I showed you, there are about 40,000 more water pixels have shown up in the last 18 years, which is a pretty large amount of surface area because 40,000 pixels would correspond to something of the order of 10,000 square kilometer of water in terms of surface area. So it makes these kind of studies much, much easier. Now, this was a MODIS-based product, and this methodology that we have can work with any kind of labels that are coming from MODIS or Landsat. So the next one I'm showing you is another website link, and you can see the link inside the slide, which allows you to see all of the water bodies that are 1/10 of a square kilometer and above. So basically, you're looking at any water body that is more than 10 hectare long, and then there are about 700,000 such water bodies that the system has. The picture that you're seeing here on the screen is just a heat map of only about 80,000 water bodies that we have found in last fall. So you will see large areas of the world that have nothing in them, but this is just because the picture is old. But the system, if you go to, would have more than 500,000 water bodies, and then you can see the size distribution. And if you were to go to this link, you will, and if you zoom in at the highest level, you will see the color that you see on the right side. But if you zoom in, you will see the circles, and the circles come in 3 different sizes: less than 1 kilometer, between 1 and 10, and more than 10 kilometers. They also would be colored, whether they are shrinking over a period of time or increasing, so blue versus brown. And for any of these water bodies, then you can sort of find the area time series as to how they're changing. And this product is constructed using both using the elevation information and correction of labels, both in space and time. Now, one of the side product of this database of more than 500,000 water bodies is that we can see all of the reservoirs that have been built in the last since 1985 through this system. So we have this global lake dynamics database for reservoirs, GLAD, and GLAD-R, which only has reservoirs. So this portion, this new link, every one of these slides has a different link. This link will take you to only the reservoirs that we have in the world. And in this one, you're seeing 3 different colors here. The blue points represent the reservoirs that were created before 1986 and were reported in GRAND. So we picked up those about 4,800 reservoirs from GRAND built before 1986. And the yellow and red points together correspond to about the same number, more than 4,000 reservoirs that were built since 1985. And of those more than 4,000 reservoirs, only about 483 are listed in the GRAND, actually the new version of GRAND that was just released a few months ago, and vast majority of them are not there. So basically, the system allows you to see the dynamics of all of these reservoirs, and also huge number of reservoirs that were not even known to the community. And the next sort of slide sort of shows you the distribution of these reservoirs in different part of the world. So this in the left side, you see the reservoirs in GLAD-R that are the previous slide was sort of showing you all of the reservoirs starting at 0.1 square kilometer and above. This one is only about reservoirs that is 1 square kilometer and above, so this is a smaller number. But you can sort of see from this slide as to where these reservoirs are, which continents they got built, and which years they got built, and what happened to the activity. Apparently, around 2000, at the turn of the century, millennia, there was a lot of activity, and which seems to be slowing down in terms of building the reservoirs. You can see these dynamics because we know the surface area and how they're changing. For all of the reservoirs built before 86 and built after 86, you can see the area in the square kilometer changes. The black line telling you collection of reservoirs, the collective area of all the reservoirs built before 86, and the red line telling you of what's happening today. Which of course, this is a much larger variation than you can see. And one of the striking trend in the last 7-8 years, all of these reservoirs are actually shrinking. So the total area is going down quite a bit. You can, of course, do this analysis for different continents because we have the information in that format. And again, you can see in South America, the reduction is most prominent. And on the very last slide, I'm going to show you just very briefly before I turn over for the questions, is to show you that, yes, indeed, we can build these downscaling from MODIS to a much higher resolution. So I'm here only showing you a single picture, not an animation on the left side for this lake, that was mapped using MODIS at 500 meter, and you can see it's a jagged shape for December 19 to 2015. And on the right side, you see a very precise shape constructed without looking at the high resolution data from the satellite, but constructed solely using this physics-guided machinery, which takes the implicit elevation information into account. We have done similar downscaling using 10-meter USGS elevation data that's available for the US. So basically, either if the elevation data is available, or if we have labels available over a period of time from which we can infer an implicit ordering, we can perform this kind of downscaling. And because we can construct this downscaling on a daily scale using the MODIS data that's available on a daily scale, we can actually use this information to create hydrographs, or even using some other techniques, construct the changes in the water volume in water bodies, which again could be used to calibrate hydrological model. So with that, I'm going to stop. And on the last slide, I'm just showing you all of the different ways, or some of the many different ways machine learning can be helpful in applications related to water. Thank you. And I guess, Jordan, maybe you can take over the control and perhaps address the questions.
Sure. All right.
So, Jordan, do you have something to add here?
Oh, no, I don't. I think this is our last summary slide, but just in case we have questions or we need to go back in the slides.
Yeah, there are some questions here. So one of the questions asked by Alex Swin, who actually I think presented a week ago, is can you discuss the advantage of the theory-guided machine learning method versus conventional data assimilation, which has the chance to continuously improve whenever you have new information?
Jordan, I can take a crack, and
Sure.
I think you will be able to provide a much fuller picture. And data assimilation is a technique that, of course, used very widely in physical sciences, and certainly one very important way of bringing data and physics together. Now, from my perspective, from the machine learning perspective, we view data assimilation as an orthogonal approach. I mean, in machine learning paradigm, there is no concept of assimilating the real-time data, and however, any approach that we have in machine learning could potentially benefit from such a paradigm. Now, what we view the machine learning paradigm is an orthogonal way of bringing physics and data together, and these methods can be augmented with assimilation paradigm in the sense that you saw the lake prediction and it's the temperature prediction of a lake, and using both the GLM, the standard physics guided machinery, the pure deep learning machinery, and the physics guided deep learning machinery, and on the machine learning side, if the real time information about the temperature of the lake, for example, for the surface area became available, it would be very interesting to see how that could be used to inform the further predictions of temperature. This is something Jordan and I have talked about. It's on our research agenda. We think it's a very exciting direction. It could really inform new research at this interface, but we haven't done that, and I think it'll be something we would love to pursue. Jordan, perhaps you can add something to it.
Yeah, I was just going to agree. I think that the forward-looking way to view how these things could work together is that it kind of, once again, isn't in either or. It would be best to think about it as a complementary future research avenue. And as Vipin mentioned, we've been thinking about different ways to combine these approaches that kind of introduce some new challenges to the architecture of these deep learning models. And so I guess it's viewed as a future kind of midterm research goals to figure out ways where those two approaches can work together and complement. And
actually, we proposed a session. There's another colleague of mine at Colorado who asked me to join in the co-provision data machine learning meets data assimilation. So this is a session we proposed for AGU. If it gets accepted, hopefully we'll have a discussion at AGU on this topic.
Cool. So another question was related, so I guess it's kind of answered already. We have a question from Vipin Shah. He asked, how does the train process differ from the pre-train process? I guess this is referring to some of what Jordan presented.
Okay.
Are the parameters of the model tweaked again?
Okay. So let me try to take a crack at it, and perhaps Jordan could follow up. So pre-training simply means that we are going to use the driver information and the output of a physical model like GLM to train a machine learning model. So machine learning model can be trained as long as you have the input and the output. Now, if the output is a real observation, then machine learning will try to mimic the physical system, the real system. If the output is coming out of a physics-based model, then machine learning will mimic the physics model. And if it's only mimicking the physics model, the best it could do is replicate the physics model, perhaps at a less computational cost when you run it eventually. It shouldn't be expected to do any better. So pre-training is simply being trained on a training wheel from lots of data coming from a physics model, no guarantee of how well you would do in observations. And when we bring in the observations, we are refining the model to conform to the reality. So basically, we are correcting the biases that may be inherent in the physics model. Jordan, perhaps you could clarify this further, since this question perhaps is best answered by you.
Yeah, no, I think that's spot on. And I guess one other caveat to bring up here is you might ask the question, why not calibrate your process-based model and use that output to pre-train the machine learning model? And for that, we have considered that approach, but it's kind of a question of where do you ultimately want your corrections to be applied? Do you use something like machine learning, which might be smarter and more flexible in applying that, or do you use the calibration of variables that you have exposed to you and maybe risk overfitting, which might take your pre-training data and turn it into something which might not improve your ultimate predictions that you're making? I hope that these two answers answered that question. Part of it I didn't quite hear, but I think that was the gist of it.
Yeah, that sounds good to me. So another question asked by Stuart Carey was that you guys mentioned some interesting patterns where groundwater and surface water levels move in opposite directions. Can you elaborate on that more, or?
Yes, certainly. I did not have those slides. I wish I did. Basically, what we did was we took the whole globe, we broke it into a degree, 1 degree by 1 degree cell. For each of those cells, we took the information that was coming out of GRACE. Basically, we took the GRACE data. And then we also, for that cell, we looked at all of the water bodies and counted the number of pixels in those water bodies. And we created a time series, basically at the same temporal resolution as GRACE. And then, and if I were giving that presentation, or if I could sort of talk to you on one-on-one, I'll show you for every location on the globe, you can click on it and you can see the two time series, one from GRACE and one from the surface area. And we created a heat map, and the heat map is bright red. That means very high correlation between these two time series. In most places, the correlation is upward of 80 to 90%. But in some places in the world, these time series are going in completely opposite direction. And some of these places are ranging from the northern Indian, the grain belt, which is where a lot of the grain is sort of grown in India. They pump a lot of water out of the ground, and they're doing a lot of aqua farming. That is, they do rice farming by pumping the water. So the water is picked up by our algorithm as a water body, but then it's being evaporated, so you're losing the water underneath. And you see that trend all the way from northern India going down to Vietnam. That is, you can sort of see in Thailand and Vietnam and Cambodia, the southern border, you can see all of those places that they have the opposite correlation. And when you zoom in on Google Earth, you find all of these farms, the aqua farms. So all of these negative relationships seem to be exactly the result of the agriculture, the human intervention. Most of the places, the groundwater and surface water is going just in the right direction.
Okay. For the GRACE, though it's a very coarse product,
Yes.
And it also has surface water as well as soil moisture and all these different water storages.
Right.
Okay, so another question. On one of the slides, you talked about application of machine learning for flood inundation mapping.
Yes. Yeah. Again, I didn't go into any further detail, but what we are doing is using this very high resolution mapping of the water bodies in time. We are creating a calibration data. So we are doing it in two different ways. One of them is to in areas where there is no calibration data available, there's no gauge data available, in a lot of developing part of the world, but also in US as well. We are creating the size of these water bodies, a time series of water bodies of this water area, time series of these water bodies, and that is serving as a hydrograph to train the model. That is, if you're building you have a hydrology model and you're sort of showing you that area got flooded, now we can go back in time for the last 30 years and see what the surface extent map was on that day and create a surface, basically hydrograph to calibrate the model. The other thing that we have not done, but I think which is doable, is that in conjunction with the elevation data that's available from many sources, including USGS and many other people who are doing LiDAR mapping, with the elevation data available at a high resolution and the surface area maps at high resolution, together we can use to compute the changes in volume of many of these reservoirs or water bodies, and they could be converted into a better information to calibrate the hydrological model. So that's exactly what I meant by that part.
Okay. My follow-up question is: you're looking at a certain discharge in time, and look at where it's inundated.
So basically, discharge. If you have the discharge information, you know exactly how to use it in a model. What I'm talking about is we can't look at the discharge, but we can look at the surface area of any body that's visible from the space.
Mm-hmm.
And if I know the changes in the surface area of the water body, I have one level of hydrograph. That means I know that if the water body is larger, the water must be more there. Second thing is, if I know the elevation at a high resolution, I can find out how the volume of the water body is changing, and that makes it even more precise. And the third thing is, for a river, let's say, if I know its width at different locations and how it's changing, people have created in hydrological community techniques to compute flow out of that information. So basically,
right.
Yeah. So using these three different types of steps, we can take the surface area maps and convert them into information that gets closer and closer to what people need for quote unquote calibrating the model.
Okay, cool.
Yeah, thank you.
Let's see. One last question asked by Chao Chen from Boise State. Have you done any machine learning, deep learning in meteorological research or downscaling?
Not yet, but there are other people who are working on it. So there are several groups. Deep learning, application of deep learning in the environmental sciences is actually gaining huge attention. So there are people at NCAR, David Gagne, and there's another person, Professor Amy, and she's at Oklahoma, University of Oklahoma. She works quite a bit on that space. If you send me an email, I'll be happy to send you directions to those people.
Okay. Okay. One last question by Steve Burgess. I think you kind of answered it. I'm not sure if you have anything to add. That is, how much did you gain with process-guided deep learning over what you could achieve with process-based models written as an example, common filtering? So basically, have you compared your method with data simulation results? I guess that's the question. And you kind of probably answered it already.
Yeah. And as I said, data simulation is about looking at real-time data, and there's an orthogonal dimension, and that's a completely different aspect. And we hope one day to merge this process-guided deep learning with data simulation. And I think they can really leverage each other as opposed to be a competition with each other.
I have a question for Jordan. For your water temperature model, what kind of model did you apply? Like the machine learning model? What is it?
So what is the deep learning element?
Yeah.
So it's a recurrent neural network with an LSTM that takes the same inputs as the process-based model. So it's the same meteorological conditions. We mirrored those so that the same data needs would exist for both, and that the same signals that would be necessary for process-based interpretation of the weather, kind of conversion into temperature change, would be available directly to the model.
Then for a lake, you have inputs from the adjacent watershed, right? So you really have a spatially distributed input of discharge and water temperature.
Yeah. Okay. I see what you're getting at. So part of this is the simplification of the system. So in order to do process-based lake and temperature models where you understand and measure all of the different water fluxes that contribute to either temperature or water level change, you would be extremely data limited. We do not have that information at scale, either through modeling or through observations, at least at the scale of modeling that we're doing here. So what we do instead is recognize that in some cases, in some systems, or in some seasons, these process-based formulations are going to be biased. And we can fix that bias by either tracking down each one of those fluxes, or we can use the power of this hybrid model to make those corrections for us. So it's kind of an approach that deals with the reality of the observing network that we have. If we had all of the fluxes measured and really great weather data, temperature is one of the easiest things to model if we have all of those fluxes captured. And we can build really great models with a process-based approach, but those are just simply not supported by the reality of our observing network, because having those data at all locations is not feasible.
So the hydrological models that you ran are distributed, and they have outputs for all those lakes? That's also pretty big by itself.
So they can be, but these systems are treated independently. So each GLM model has no knowledge of the upstream lakes if they're connected in a network. That independence is powerful because it lets us tackle this problem. But yes, if we connected that network more directly, we could potentially improve the predictions. But I will add that in temperature system, or in lake systems, the inflow outflow is definitely quite relevant to understanding the water budget. Its impact on the temperature is less in many cases than the impact of the meteorology. So versus if we were doing stream and river temperature prediction and we excluded those network components, we excluded upstream contributions, then we'd be doing a disservice to the prediction, because we'd be robbing it of that critical information. So it's kind of taking advantage of the different, the relevant size of the fluxes and the difference between lakes and reservoirs and streams and rivers, where lakes and reservoirs, the important gradients to understand in many cases for temperature is the vertical gradient. So the thermal stratification vertically.
Cool. Thanks. So those are all the questions that I can find. Please, if you want to talk about the following activities. Next week, we will have the last and final Big Data Machine Learning and Hydrology webinar by Dr. Xu by UC Irvine, who is one of the first users of deep learning in hydrology. Elise, do you want to talk about the conference?
Yeah, sure. So let me take presenter mode back from Vipin and show my screen. Let's see. Sorry for the little delay. So Xiaopeng mentioned the last talk for the series, but I want to mention the CUAHSI 2019 Conference on Hydroinformatics. It'll be taking place at the end of July in Provo, Utah. Chao Peng is a keynote speaker along with several others. We have 6 in total. We are still accepting poster abstracts. So if you are a student or scientist who'd like to present their work in our poster session, feel free to submit an abstract through the conference website. And we are offering, on a first-come, first-served basis, $750 travel grants. And we do have a lot of them left, so please do take advantage of it. It's a good conference, and I think it's a very diverse topics that we have going on. And we will announce those topics within the next few weeks on our conference website. So do stay tuned. And then for everyone else who doesn't want to present a poster, we do have registration deadlines. So June 15th is the early bird, and then July 15th is regular. And then if you're a quasi member, if your university is a quasi member, you do have a $50 discount to these conferences and workshops that we hold. So.
Thanks, Liz. Well,
Yep.
Well, thanks to 2 speakers. I just clap on my end. No, I can't hear the crowd clapping. Thank you, and see you next week.
All right. Thank you.